We've been talking a lot about the science of how things move. You throw a ball in the air and there are ways to predict exactly how it will fall. But there's something we've been leaving out: forces, and why they make things accelerate. And for that, we're going to turn to a physicist you've probably heard of: Isaac Newton. With his 3 laws published in 1687 in his book Principia, Newton outlined his understanding of motion, and a lot of his ideas were totally new. Today, more than 300 years later, if you're trying to describe the effects of forces on just about any everyday object, a box on the ground, a reindeer pulling a sleigh, or an elevator taking you up to your apartment, then you're going to want to use Newton's laws. And yes, I'll explain the reindeer thing later. Newton's first law is all about inertia, which is basically an object's tendency to keep doing what it's doing. It's often stated as an object in motion will remain in motion and an object at rest will remain at rest unless acted upon by a force. Which is just another way of saying that to change the way something moves, to give it acceleration, you need a net force. So how do we measure inertia? Well, the most important thing to know is mass. Say you have 2 balls that are the same size, but one is an inflatable beach ball and the other is a bowling ball. The bowling ball is going to be harder to move and harder to stop once it's moving. It has more inertia because it has more mass. Makes sense, right? More mass means more stuff, with a tendency to keep doing what it was doing before your force came along and interrupted it. And this idea connects nicely to Newton's second law. Net force is equal to mass times acceleration. Or, as an equation, F net equals ma. It's important to remember that we're talking about net force here, the amount of force left over once you've added together all the forces that might cancel each other out. Let's say you have a hockey puck sitting on a perfectly frictionless ice rink, and I know they're not usually perfectly frictionless, but stick with it. If you're pushing the puck along with a stick, that's a force on it that isn't being cancelled out by anything else, so the puck is experiencing acceleration. But when the puck is just sitting still, or even when it's sliding across the ice after you've pushed it, then all the forces are balanced out. That's what's known as equilibrium. An object that's in equilibrium can still be moving, like the sliding puck, but its velocity won't be changing. It's when the forces get unbalanced that you start to see the exciting stuff happen. And probably the most common case of a net force making something move is the gravitational force. Say you throw a 5-kilogram ball straight up in the air and then, get out of the way because that could really hurt if it hits you. But the force of gravity is pulling down on the ball, which is accelerating downward at a rate of 9.81 meters per second squared. So the net force is equal to ma. But the only force acting here is gravity. This means that if we could measure the acceleration of the ball, we'd be able to calculate the force of gravity. And we can measure the acceleration. It's 9.81 meters per second squared, the value we've been calling small g. So the force of gravity on the ball must be 5 kilograms, which is the mass of the ball, times small g, which comes to 49.05 kilograms times meters per second